Tonight, we turn our attention to something that surrounds us completely, yet has never once been seen. Dark matter makes up most of the mass in the universe. It holds galaxies together, shapes the large-scale structure of the cosmos, and leaves its signature in nearly every measurement astronomers make. And yet, after nearly a century of investigation, no one has ever directly observed a single particle of it. We will move through this topic gradually. We will begin with the first observations that suggested something was missing from our understanding of the universe. We will consider how galaxies rotate, how clusters of galaxies hold together, and what the geometry of the cosmic web tells us about matter we cannot see. We will also look at the leading candidates for what dark matter might actually be, and at the experiments quietly searching for it right now. There is no rush. Each idea will have time to settle before we move to the next. This is Sleepy Time Universe, where we explore the cosmos slowly and without urgency. Get comfortable as we spend the next several hours considering one of the deepest questions in modern science. What is dark matter, and how does something invisible come to shape everything that exists? The story of dark matter does not begin with a dramatic discovery. It begins with a quiet discrepancy, a number that did not quite match, an observation that refused to fit the existing picture. In the early 20th century, astronomers were still coming to terms with the true scale of the universe. The Milky Way had long been assumed to contain everything worth studying. Then, in the 1920s, it became clear that the faint spiral smudges visible through telescopes were not clouds of gas within our own galaxy. They were entire galaxies in their own right, each containing hundreds of billions of stars, each separated from us by distances almost too large to hold in the mind. With this new picture came new questions. If these galaxies existed in such enormous numbers, how were they distributed through space? How did they move relative to one another? And did the laws of gravity, so well tested within our own solar system, continue to apply across these vast distances? The first serious hint that something was wrong came from a Swiss astronomer named Fritz Zwicky. In 1933, Zwicky was studying the Coma Cluster, a large collection of galaxies bound together by gravity, roughly 320 million light-years from Earth. He measured the velocities of individual galaxies within the cluster, how fast they were moving relative to one another, and then calculated how much mass would be needed to hold the cluster together at those speeds. The answer he got was deeply uncomfortable. The visible matter in the Coma Cluster, all the stars in all the galaxies, all the gas between them, everything that could be observed, accounted for only a small fraction of the mass required. To keep the cluster gravitationally bound, there would need to be far more mass than anything visible could explain. Zwicky called this missing material Dunkelmaterie, dark matter. At the time, the observation was noted and largely set aside. Measurements were imprecise. There were plausible alternative explanations. Perhaps there was gas or faint stars that had simply not been detected. Zwicky was known for provocative claims, and this one, while interesting, did not immediately reshape the field. It would take several more decades and a different line of evidence entirely before dark matter began to seem not just possible, but necessary. The second, and far more persuasive line of evidence came from the rotation of individual galaxies. To understand why this matters, it helps to think about how rotation works in a system where mass is concentrated at the center. Consider our solar system. The Sun contains more than 99% of all the mass in the solar system. The planets orbit around it, and because nearly all the mass is at the center, The speed of each planet's orbit depends on its distance from the Sun in a very specific way. Planets close to the Sun move quickly. Planets far from the Sun move slowly. Mercury completes an orbit in 88 days. Neptune takes 165 years. This pattern, faster orbits close to the center, slower orbits farther out, is what physicists call a Keplerian rotation curve, named after Johannes Kepler, who first described the mathematical relationship between orbital distance and orbital speed. When astronomers first began measuring the rotation of spiral galaxies, they expected to find something similar. Most of the visible mass in a spiral galaxy, most of the stars, most of the bright material, is concentrated toward the center, in the bright bulge and the inner disk. By the logic of Keplerian rotation, stars near the center should orbit quickly, and stars in the outer regions of the galaxy, far from most of the mass, should orbit more slowly. What they found instead was something quite different. In the 1960s and 1970s, an astronomer named Vera Rubin, working with her colleague Kent Ford, developed techniques precise enough to measure the rotation speeds of stars at different distances from the centers of spiral galaxies. What she found, first in the Andromeda Galaxy, and then in galaxy after galaxy, was that the rotation curve was flat. Stars in the outer regions of galaxies were not slowing down as distance increased. They were moving at roughly the same speed as stars much closer to the center, and in some cases, the outermost stars were moving faster than any reasonable distribution of visible mass could explain. This was not a small discrepancy. It was not the kind of thing that could be explained by a missing cloud of gas or a population of faint stars. The outer regions of galaxies were rotating far too quickly. Something was providing gravitational force in the outer disk and beyond. Something that could not be seen. Rubin's measurements, repeated across dozens of galaxies and confirmed by independent groups, made the case for dark matter difficult to dismiss. The flat rotation curves were consistent and reproducible. Whatever was causing them was not a measurement error. It was a physical reality. The picture that emerged from these observations was striking. Visible galaxies, the luminous disks of stars we can photograph and study, appear to be embedded within much larger, roughly spherical structures of dark matter. These structures are called dark matter halos. The visible part of a galaxy, the part we can see, occupies only the central region of a far larger dark matter distribution that extends well beyond the visible edge of the disk in every direction. Our own Milky Way is no exception. The stars and gas and dust that make up the visible galaxy extend perhaps 50,000 light-years from the center. The dark matter halo surrounding it may extend 10 times farther or more. Most of the mass associated with our galaxy is invisible, spread through a vast sphere that we can only infer from its gravitational effects. This is a significant revision to how we think about galaxies. What we see when we look at a spiral galaxy in a photograph, the beautiful disk, the spiral arms, the glowing core, is in some sense the visible tip of a much larger invisible structure. The galaxy we can photograph is embedded within a dark matter halo many times its size, and it is the gravitational influence of that halo that governs how the galaxy moves, how it forms stars, and how it interacts with neighboring galaxies. The work of Rubin and Ford, combined with Zwicky's earlier observations of galaxy clusters, established dark matter as a serious scientific problem, rather than a curiosity. Something real was out there, affecting the universe in measurable ways. The challenge was to understand what it was. We will consider that question in the chapters ahead. But before we move on, it is worth pausing for a moment to appreciate the nature of what had been discovered, or rather, inferred. Dark matter had not been found in the usual sense. No one had detected a particle, captured a signal, or seen an image. What had been established was a pattern of gravitational effects that could not be explained by anything visible. The evidence for dark matter was, from the beginning, entirely indirect. This is not unusual in science. Many of the most important entities in physics were first inferred from their effects before they were directly detected. The planet Neptune was predicted from irregularities in the orbit of Uranus before anyone pointed a telescope at it. The Higgs boson was a theoretical necessity for decades before the Large Hadron Collider confirmed its existence. Dark matter followed a similar path. First a gravitational anomaly, then a pattern of anomalies, then a structure of anomalies so consistent and widespread that the existence of something real became the most economical explanation. The flat rotation curves of galaxies remain today one of the most compelling pieces of evidence for dark matter. They have been measured for hundreds of galaxies across a wide range of sizes, ages, and types, and in every case, the pattern holds. The visible, matter alone cannot account for the motion. Something else is present, distributed throughout the halo, exerting gravitational force without emitting any light. As you settle in and let these ideas drift through your mind, consider what it means to live inside one of these structures. Every star you can see in the night sky, every galaxy visible through a telescope, exists within a vast sea of invisible matter. The structure of the universe, the way galaxies cluster, the way filaments form between them, the way the cosmos organizes itself on the larger scales, is shaped not primarily by the matter we can see, but by matter that remains, for now, beyond our direct perception. That is where we begin. In the chapters ahead, we will follow the evidence further, moving from individual galaxies to galaxy clusters, from clusters to the large-scale structure of the universe, and from there to the deepest questions about what dark matter might actually be made of. To understand why dark matter became a scientific necessity rather than a speculative idea, it helps to understand precisely what astronomers were measuring when they studied galaxy rotation and why the results were so difficult to explain away. A galaxy is not a solid object. It does not rotate the way a wheel rotates, with every part completing one revolution in the same amount of time. A galaxy is more like a vast, loosely organized collection of individual stars, each following its own orbit around the gravitational center of the galaxy. The speed at which any given star orbits depends on how much mass lies between that star and the center of the galaxy. This is a consequence of Newton's law of gravity, which describes with great precision how objects move under the influence of gravitational force. When mass is concentrated at the center of a system, as it is in our solar system, where the sun dominates, the gravitational force experienced by an orbiting object decreases, predictably, as distance increases. A planet twice as far from the sun feels only 1/4 of the gravitational pull. To remain in a stable orbit at that greater distance, it must move more slowly. This is why the outer planets of our solar system move so much more sedately than the inner ones. The same logic should apply to galaxies, with one complication. Unlike the solar system, where nearly all the mass is concentrated in a single central object, a galaxy distributes its mass across a disk of stars and gas, with a concentration toward the center, but a significant amount spread throughout the disk. Accounting for this distribution, astronomers could still make predictions about how orbital speed should change with distance from the galactic center. The prediction was not identical to the solar system case, but the general shape was similar. orbital speed should rise in the inner regions as more mass is enclosed within the orbit, peak at some intermediate distance, and then decline gently in the outer regions as the enclosed mass levels off. This predicted pattern is called the rotation curve of a galaxy, a graph of orbital speed on the vertical axis against distance from the galactic center on the horizontal axis. For a galaxy whose mass is distributed roughly as its light suggests, the rotation curve should show a rise, a peak, and then a gradual decline. The decline in the outer regions is the key prediction. As stars move farther from the center, past most of the visible mass, they should slow down. Vera Rubin did not set out to challenge fundamental assumptions about the universe. She was drawn to galaxy rotation because it was a tractable problem, something that could be measured with the technology available in the late 1960s and early 1970s, given sufficient patience and precision. Together with her colleague Kent Ford, who had developed an exceptionally sensitive spectrograph, she set about measuring the rotation curves of spiral galaxies with greater accuracy than had previously been achieved. The technique they used relies on the Doppler effect. When a source of light is moving toward an observer, the light waves are compressed and the light appears shifted toward the blue end of the spectrum. When the source is moving away, the waves are stretched and the light is shifted toward the red end. By measuring the precise wavelength of light emitted by stars and gas clouds at different positions within a galaxy, astronomers can determine how fast each region is moving toward or away from us. For a galaxy oriented roughly edge-on to our line of sight, one side of the galaxy will be rotating toward us, and the other side will be rotating away, producing a characteristic pattern of blue and red shifts across the disk. Rubin and Ford applied this technique to the Andromeda galaxy first, our nearest large galactic neighbor. The results were puzzling. Rather than declining in the outer regions, the rotation curve remained flat. Stars at the outermost measurable edges of the disk were moving at roughly the same speed as stars much closer to the center. The expected decline was simply not there. They checked their measurements. They refined their techniques. They moved on to other galaxies, NGC 2403, NGC 3109, a growing list of spirals of various sizes and orientations. In galaxy after galaxy, the rotation curve was flat. The decline that Newton's gravity demanded, given only the visible mass, was absent. By the late 1970s, Rubin and Ford had measured the rotation curves of dozens of spiral galaxies, and the result was consistent enough to be considered a pattern rather than an anomaly. The flat rotation curve was not a feature of one unusual galaxy. It was a general property of spiral galaxies as a class. What does a flat rotation curve imply? The mathematics are straightforward, if the conclusions are unsettling. For a rotation curve to remain flat at large distances from the galactic center, the mass enclosed within each orbital radius must continue to increase proportionally with that radius, even in regions where little or no visible matter is present. In other words, there must be mass in the outer regions of galaxies, mass that does not shine, does not emit radio waves, does not absorb background light in any way that had been detected. Invisible mass, distributed in a roughly spherical halo extending far beyond the visible disk. The amount of this invisible mass implied by the flat rotation curves was substantial. In a typical spiral galaxy, the dark matter halo may contain 5 to 10 times more mass than all the visible stars and gas combined. The luminous galaxy, the part we can photograph, the part that inspired generations of astronomers and amateur stargazers, represents only a modest fraction of the total mass of the system it belongs to. This was a difficult result to accept, and it was not accepted immediately. Some astronomers proposed that Newton's law of gravity itself might need modification at the low accelerations typical of galactic outskirts. This idea, known as modified Newtonian dynamics, or MOND, attracted a dedicated following and continues to be investigated today. Others suggested that the missing mass might be accounted for by dim objects, faint dwarf stars, brown dwarfs, black holes, that simply had not been detected. These alternatives were not unreasonable, and they deserved serious investigation. But over the following decades, as new lines of evidence accumulated, the dark matter interpretation gained ground. The flat rotation curves were real. The alternatives struggled to explain them consistently across the full range of galaxy types and masses. And independent evidence from entirely different astronomical observations began pointing to the same conclusion. The rotation curve evidence has a quality that makes it particularly persuasive. It is not a statistical argument or a subtle inference. It is a direct measurement. You measure how far stars are moving at different distances from a galactic center. You plot those measurements, and the curve is flat when it should decline. The disagreement between observation and prediction is not small. It is not hidden in the noise. It is a clear, reproducible, systematic discrepancy that runs across hundreds of measured galaxies. Vera Rubin spent much of her career working on this problem, and she was remarkably measured in how she discussed it. She did not claim to know what dark matter was. She was careful to describe what the observations showed and to leave open the question of interpretation. What she was certain of was that the observations were real, that they were telling us something important, and that the universe contained far more than could be accounted for by the light reaching our telescopes. That disposition, precise observation, honest acknowledgement of what the data shows, patience with questions that cannot yet be answered, is a useful posture to carry into the rest of this exploration. Dark matter is a scientific problem in the best sense. The evidence for its existence is strong. The question of what it actually is remains genuinely open. Both of those things can be true simultaneously, and neither undermines the other. As you rest and let these ideas settle, consider the flatness of that rotation curve, not as a graph on a page, but as a physical reality, star after star, orbiting at the same speed, whether it is close to the galactic center or far out in the dim reaches of the disk, held there by the gravity of something that offers no light in return. The universe is generous with its mass and reluctant with its visibility. The flat rotation curves of spiral galaxies told astronomers that something invisible was present in the outer regions of those galaxies. But what does this invisible material actually look like? How is it distributed? What is its shape and extent? And what role does it play in the life of the galaxy it surrounds? The answers to these questions have come from a combination of observational data and computer simulation, and they have given us a reasonably detailed picture of what dark matter halos look like, even though we have never directly observed one. The first thing to understand about a dark matter halo is that it is not a disk. Visible galaxies are predominantly flat. Their stars and gas settle into a rotating disk because angular momentum encourages matter that is colliding and interacting to spread into a plane. Dark matter, by contrast, does not interact with itself or with ordinary matter in any way other than gravity. It does not collide. It does not lose energy through radiation. It cannot cool and condense. As a result, it does not flatten into a disk. It remains in a roughly spherical distribution, extended in all directions around the center of mass. This is a subtle but important distinction. When you look at a photograph of a spiral galaxy, you are seeing the disk, the thin, flat, luminous structure that contains the stars and gas. This disk is embedded within a much larger, roughly spherical dark matter halo that extends in every direction, including above and below the plane of the disk. The halo is not a ring or a shell. It is a three-dimensional volume of invisible mass that dwarfs the visible galaxy in both size and total mass. The density of the dark matter halo is not uniform. It is highest near the center of the galaxy and decreases with distance, though the rate of decrease is gentler than the decrease in visible matter density. The profile of a typical dark matter halo, how density varies with radius, has been studied extensively using computer simulations of galaxy formation, and a particular mathematical form called the Navarro-Frenk-White profile has been found to fit simulated halos remarkably well. According to this profile, density falls off as roughly the inverse square of the radius in the outer regions, producing the gravitational effect that generates flat rotation curves. The exact profile of real dark matter halos is a matter of ongoing investigation. Simulations predict a sharp increase in density toward the very center of a halo, a so-called cusp. But observations of some galaxy types, particularly dwarf galaxies, suggest that density may actually flatten toward the center into what is called a core. This tension between simulated cusps and observed cores is one of the active research questions in dark matter astrophysics, and it may have implications for the nature of dark matter particles themselves. The total extent of a dark matter halo is difficult to measure directly because, at large distances, the density becomes too low to produce detectable gravitational effects on any individual tracer. For the Milky Way, estimates based on the motions of satellite galaxies and distant stars suggest the halo extends somewhere between 200,000 and 600,000 light-years from the galactic center, compared to the roughly 50,000 light-year radius of the visible stellar disk. The halo is vast by any measure. The mass of the Milky Way's dark matter halo is estimated at somewhere between 1 trillion and 2 trillion times the mass of the Sun. The total mass of all the visible stars in the Milky Way is roughly 50 to 60 billion solar masses. So the dark matter halo outweighs the visible stellar content of the galaxy by a factor of roughly 20 to 40. The galaxy we see is a small luminous core within an enormous invisible structure. Dark matter halos are not smooth, featureless spheres. Computer simulations predict that halos have substructure, smaller concentrations of dark matter called subhalos, distributed throughout the larger halo. These subhalos are the remnants of smaller halos that have been absorbed during the assembly of the larger halo through mergers over cosmic time. The Milky Way's halo is predicted to contain hundreds of thousands of these subhalos, many of which may correspond to the dwarf satellite galaxies that orbit our galaxy, while many others may contain too little visible matter to have formed any stars at all. This substructure is one of the predictions of the standard model of dark matter, known as cold dark matter, or CDM, that has proven most difficult to confirm observationally. The model predicts far more satellite galaxies around a galaxy like the Milky Way than have actually been detected, a discrepancy known as the missing satellites problem. This might mean that most small halos simply fail to form stars and remain invisible, or it might indicate that the cold dark matter model needs refinement. Observations with increasingly sensitive telescopes continue to find new ultra-faint dwarf galaxies around the Milky Way, gradually closing the gap. The shape of dark matter halos is also a subject of investigation. Pure dark matter simulations tend to produce halos that are not perfectly spherical, but somewhat elongated, described mathematically as triaxial, having 3 different axis lengths. However, the gravitational influence of the ordinary matter in the central disk can reshape the inner portions of the halo over time. The interplay between the dark matter halo and the visible matter it contains is a complex and ongoing area of research. One of the most important functions of the dark matter halo is that it provided the initial gravitational well into which ordinary matter fell when galaxies were first forming, billions of years ago. In the early universe, dark matter began clumping together first, because it was not subject to the radiation pressure that slowed the clumping of ordinary matter. These dark matter overdensities became the seeds around which visible matter later gathered, cooled, and formed stars. Without the prior existence of dark matter halos, galaxies as we know them might never have formed at all. The halo is not merely a passive companion to the visible galaxy. It was, in a real sense, the scaffold on which the galaxy was built. This developmental role of dark matter halos connects to one of the most active areas of modern cosmology, understanding how galaxies form and evolve over cosmic time, and how the properties of dark matter govern the properties of the galaxies that form within halos of different masses. Large halos tend to host large galaxies. Small halos tend to host small galaxies, or no galaxy at all. The mass function of dark matter halos, how many halos of each mass exist, determines much of what we observe when we survey the galaxy population of the universe. The picture that emerges from all of this is one of nested structures. Visible galaxies are embedded in dark matter halos. Dark matter halos are arranged in a larger network, a cosmic web of filaments and nodes. And the properties of individual visible galaxies are shaped, to a significant degree, by the properties of the dark matter halos they inhabit. To understand galaxies, you must understand halos. And to understand halos, you must grapple seriously with the nature of dark matter. Let the image of the halo settle in your mind as you rest. A vast, roughly spherical volume of invisible mass, extending far beyond the light of the stars it contains, shaped by gravity alone, ancient and patient. The visible galaxy, brilliant, intricate, wheeling slowly in the dark, is nested within it like a lamp inside a room. We see the lamp. The room is inferred. Individual galaxies are not uniformly scattered across space. They gather in groups and clusters, bound together by gravity into structures that can contain anywhere from a few dozen to several thousand galaxies. These galaxy clusters are among the largest gravitationally bound structures in the universe, and they have provided some of the most compelling evidence for dark matter that we possess. Fritz Zwicky's observation of the Coma cluster in 1933 was the first indication that something was missing from our accounting of cosmic mass. His argument was straightforward. He measured the velocities of individual galaxies within the cluster, applied the virial theorem, a mathematical relationship between kinetic energy and gravitational potential energy in a stable system, and calculated how much mass would be needed to keep the cluster gravitationally bound at those velocities. The answer was far more than the mass of all the visible galaxies combined. Zwicky's calculation was roughly correct, though his estimate of the discrepancy was larger than modern values, because he used an older, less accurate value for the Hubble constant. Contemporary measurements confirm that galaxy clusters contain roughly 5 to 10 times more mass than can be accounted for by their visible galaxies and the hot gas between them. Dark matter makes up the majority of the mass in galaxy clusters, just as it does in individual galaxies. Galaxy clusters are particularly useful for dark matter research because they are large enough to be studied by multiple independent methods simultaneously. The velocities of member galaxies provide one mass estimate. The temperature and distribution of the hot gas that permeates the cluster, gas so hot that it emits X-rays, provides another. Gravitational lensing, which we will explore in the next chapter, provides a third. When these independent methods are applied to the same cluster, they tend to agree, reinforcing confidence in the overall picture. The hot intracluster gas deserves particular attention. Galaxy clusters are filled with a diffuse plasma, gas that has been heated to tens of millions of degrees by the gravitational compression of falling into the cluster's potential well. This gas is so hot that it emits strongly in X-rays, and X-ray observatories in space have mapped its distribution in thousands of clusters. The mass of this gas, while significant, is still not enough to explain the cluster's total gravitational mass. Something else must be present. The most dramatic and widely cited piece of evidence for dark matter in galaxy clusters comes from a system known as the bullet cluster. This system, located about 3.7 billion light-years from Earth, is actually two galaxy clusters that have passed through each other, a cosmic collision on an enormous scale. The collision happened roughly 150 million years ago, and the aftermath has been studied extensively because it provides an unusually clear separation of different types of matter. When the two clusters collided, different components of each cluster behaved differently. The individual galaxies in each cluster, relatively small and widely spaced compared to the overall size of the cluster, passed through the collision largely unaffected, like two swarms of bees flying through each other. The hot intergalactic gas in each cluster, however, is much more diffuse and widespread. When the gas clouds of the two clusters met, they interacted electromagnetically, slowing each other down through ram pressure and shock waves. The gas was left behind near the point of collision, heated further by the interaction, and glowing brightly in X-rays. What happened to the dark matter? If dark matter interacts only through gravity, as the simplest models predict, then it should have behaved more like the galaxies than like the gas. It should have passed through the collision largely without interaction, continuing forward with the galaxies of each cluster rather than piling up at the collision point. Observations of the bullet cluster confirm exactly this picture. X-ray observations show the hot gas concentrated near the center, between the two clusters. Gravitational lensing observations, which map the distribution of total mass regardless of whether it emits light, show the mass concentrated away from the center, associated with the galaxies of each cluster rather than the gas. The mass does not follow the gas, it follows the galaxies. This separation of mass from gas in the bullet cluster is difficult to explain without dark matter. If the missing mass was somehow made of ordinary matter, gas that simply had not been detected, then it would have been slowed by the collision just as the observed gas was. The fact that the mass moved through the collision while the gas was left behind is precisely what you would expect if most of the mass is in a form that does not interact electromagnetically, only gravitationally. The bullet cluster has become one of the most reproduced images in modern cosmology, a pink X-ray glow in the center, flanked by blue regions indicating mass from gravitational lensing, with the visible galaxies coinciding with the blue regions. It tells a clear story, and it is a story in which dark matter is not peripheral but central. Since the original bullet cluster paper, several other merging cluster systems have been studied with similar techniques, and the pattern holds. Mass, mapped by gravitational lensing, tends to follow the galaxies through collisions rather than staying with the gas. The electromagnetic interaction that slows the gas does not slow whatever the dark matter is made of. There is a subtlety worth acknowledging here. The bullet cluster and similar systems provide strong evidence that most of the mass in galaxy clusters is not in the form of hot gas or stars. They also constrain how strongly dark matter particles can interact with each other. If dark matter interacted significantly with itself, the dark matter halos of the two clusters would also have been slowed by the collision, separating from the galaxies. The fact that the mass follows the galaxies limits the self-interaction cross-section of dark matter particles to a small value. This self-interaction constraint is interesting because some proposed modifications to the standard cold dark matter model involve giving dark matter some small degree of self-interaction. Colliding cluster systems like the bullet cluster provide among the strongest constraints on this possibility, though there is still room within the observations for a modest level of self-interaction that could address some of the small-scale structure problems mentioned earlier. Galaxy clusters also provide a natural laboratory for testing the consistency of dark matter across cosmic scales. A dark matter model that works for individual galaxies must also work for clusters and for the cosmic web on even larger scales. The evidence from clusters is consistent with the evidence from galaxy rotation curves, which is consistent with the evidence from the cosmic microwave background, which we will discuss later. This consistency across scales, across independent measurement methods, and across independent research groups is one of the most compelling aspects of the dark matter case. As you rest and listen, let your mind range across the scale of what we have been considering. Individual galaxies, each containing hundreds of billions of stars, are themselves embedded in dark matter halos. Those halos are part of groups and clusters, which are themselves the nodes of a vast cosmic web. At every scale, on every level, the accounting does not balance without including matter that cannot be seen. The universe is, by mass, predominantly made of something we have never directly detected. A massive object will be bent toward that. A massive object will be bent toward that object, following the curvature of space-time rather than traveling in a straight line. This effect, gravitational lensing, was first confirmed during a solar eclipse in 1919, when the apparent positions of stars near the Sun were observed to be slightly shifted from their true positions, exactly as Einstein's equations predicted. Gravitational lensing has since become one of the most powerful tools in observational cosmology, and for dark matter research, it offers something uniquely valuable: the ability to map the distribution of mass in the universe regardless of whether that mass emits any light. A dark matter halo bends light just as effectively as an equal mass of luminous stars would. By measuring how light from distant background galaxies is distorted by intervening mass, astronomers can reconstruct the mass distribution of everything between us and those background galaxies, including mass that would be completely undetectable by any other means. The physics of gravitational lensing comes in several regimes, depending on how close the light passes to the lensing mass and how massive the lens is. At the strongest extreme, a sufficiently massive concentration of mass aligned closely with a background source can produce multiple images of that source, or distort it into arcs and rings. This is called strong gravitational lensing. At the opposite extreme, a more diffuse distribution of mass produces a subtler effect, a slight coherent distortion of background galaxy shapes that can only be detected statistically by analyzing the shapes of thousands or millions of background galaxies simultaneously. This is called weak gravitational lensing. Both regimes have proven enormously useful for studying dark matter. Strong lensing, because it is dramatic and visually striking, was the first to be widely recognized. Hubble Space Telescope images of massive galaxy clusters routinely show background galaxies stretched into arcs curving around the cluster center. Direct visual evidence that the cluster contains enough mass to bend light dramatically. The positions and curvatures of these arcs can be used to reconstruct a map of the mass distribution within the cluster, and such maps consistently show that the mass is much more extended and more massive than the visible galaxies alone would suggest. Weak gravitational lensing is more subtle, but in some ways more powerful. Any patch of sky, when photographed deeply enough, reveals thousands of background galaxies at a range of distances. These galaxies have a variety of intrinsic shapes, some round, some elongated, pointing in various directions. In the absence of lensing, the orientations of these galaxies should be essentially random, showing no preferred direction. In the presence of lensing, the gravitational influence of intervening mass introduces a small but coherent preferred alignment. Galaxies are very slightly stretched tangentially around concentrations of mass. This signal is tiny for any individual galaxy, far smaller than the intrinsic variation in galaxy shapes, but it becomes detectable when averaged over large numbers of galaxies. The practical challenge of weak gravitational lensing is considerable. The signal is only a few % of the level of noise from intrinsic galaxy shapes, instrumental effects, and atmospheric distortion. Extracting it requires precise measurement of galaxy shapes, careful modeling of all systematic effects, and statistical analysis of enormous galaxy catalogues. Modern weak lensing surveys use tens of millions of galaxy images to map the distribution of mass across large regions of the sky. The maps that emerge from these analyses are striking. They show the distribution of total mass, dark matter plus ordinary matter, across cosmic scales, and they reveal a web-like structure of filaments, nodes, and voids that closely matches the predictions of dark matter models. The correspondence between the observed mass distribution and the predictions of simulations that include dark matter is one of the most powerful validations of the dark matter paradigm. One of the most impressive applications of gravitational lensing to dark matter research is the production of three-dimensional maps of the dark matter distribution. Because background galaxies are at a range of distances, and because the lensing effect of intervening mass depends on the distances between observer, lens, and source, it is possible, with sufficient data, to reconstruct not just a two-dimensional projected map, but a three-dimensional volume map of the mass distribution. These tomographic lensing analyses have been carried out by several major surveys, and they reveal the large-scale structure of the dark matter web extending across billions of light years. Gravitational lensing has also been used to search for dark matter concentrations that contain no visible galaxies at all. If dark matter exists in halos that sometimes fail to form any stars, those halos should still produce lensing effects. Several candidate dark matter-dominated structures have been identified through lensing in regions with little visible matter, though interpreting these observations is complicated by the presence of ordinary matter at various distances along the line of sight. A particularly elegant application of gravitational lensing involves the study of individual galaxy halos. When a foreground galaxy is well aligned with a background galaxy, the background galaxy can be distorted into an arc or ring by the lensing effect of the foreground galaxy and its dark matter halo. By modeling the distortion, astronomers can measure the mass distribution of the foreground galaxy's halo, including the dark matter content. This technique, called galaxy-galaxy lensing, has been applied to millions of galaxy pairs from large surveys and provides statistical constraints on how dark matter halo mass scales with galaxy properties such as luminosity, color, and morphology. The results from galaxy-galaxy lensing are consistent with the rotation curve evidence. Galaxies are embedded in halos that are much more massive than the visible galaxy alone. The ratio of halo mass to stellar mass depends on the type of galaxy, with the most and least massive galaxies being the least efficient at converting their available mass into stars. The connection between dark matter halo properties and the visible galaxy that inhabits the halo is a rich area of investigation, with implications for understanding how galaxies form and evolve. Gravitational lensing also played a central role in the bullet cluster analysis described in the previous chapter. The maps of total mass, used to demonstrate that the mass follows the galaxies rather than the gas, were produced by weak gravitational lensing of background galaxies. Without lensing, there would have been no way to map the mass distribution independently of assumptions about its composition, and the bullet cluster argument would have been much less compelling. Looking forward, gravitational lensing is expected to play an increasingly important role in dark matter research. Upcoming wide-field space telescopes will image billions of galaxies with sufficient precision to produce weak lensing maps of unprecedented quality, covering a substantial fraction of the entire sky. These surveys will enable the most precise measurements yet of the large-scale distribution of dark matter, providing stringent tests of cosmological models and potentially revealing subtle signatures of dark matter properties that are beyond the reach of current data. There is something aesthetically pleasing about gravitational lensing as a tool for studying dark matter. It does not require dark matter to emit anything, interact with anything, or do anything other than have mass. It only requires that mass of any kind curves space-time. Dark matter curves space-time. The curvature distorts light. We measure the distortion. From that measurement, we infer the mass. It is a chain of inference that uses only the most fundamental property of mass, its gravitational influence, to make the invisible legible. As you settle further into rest, consider the light reaching us from distant galaxies, light that has traveled for billions of years, passing through the gravitational fields of halos and filaments and clusters along the way. Each photon of that light carries a small record of every gravitational influence it encountered on its journey. When we photograph those distant galaxies and notice that their shapes are very slightly aligned, we are reading that record. We are decoding, from the distorted faces of ancient light, the map of invisible mass that light passed through on its way to us. The universe writes in gravity. We are learning to read. If you could step outside the universe and look at it from a great distance, the first thing you would notice is not the galaxies. You would notice the structure. The universe, on its larger scales, is not a smooth, uniform distribution of matter. It is organized into a vast network of filaments, sheets, and nodes, separated by enormous regions of near emptiness. Astronomers call this structure the cosmic web, and it is one of the most striking features of the observable universe. The cosmic web consists of several distinct components. Filaments are the long, thin strands of matter that form the backbone of the structure. They stretch for tens or hundreds of millions of light years, connecting nodes where multiple filaments intersect. At the nodes sit galaxy clusters, the largest gravitationally bound structures in the universe, where thousands of galaxies are gathered together. Between the filaments and nodes are sheets, slightly flattened regions of moderate density that contain smaller groups and individual galaxies. And filling the majority of the volume of the universe are voids, enormous regions of near-empty space where very little matter exists. The scale of this structure is difficult to hold in mind. A single filament of the cosmic web might stretch for 300 million light-years. The voids between filaments can span 300 million light-years across, containing only a handful of galaxies, where filaments would contain thousands. The Milky Way sits within a modest filament, part of a larger structure called the Laniakea supercluster, which itself represents just one node in the broader web. The cosmic web was not always apparent. For most of the 20th century, the distribution of galaxies across the sky was known only in 2 dimensions. Astronomers could measure where galaxies appeared on the sky, but without distance information, they could not reconstruct the 3-dimensional structure. That changed with the development of large redshift surveys, which measured the distances to hundreds of thousands of galaxies by observing how their light was shifted toward the red end of the spectrum by the expansion of the universe. When the positions and distances of those galaxies were plotted in 3 dimensions, the cosmic web emerged with unmistakable clarity. The first clear picture came from the Center for Astrophysics Redshift Survey in the 1980s, which revealed the now famous Great Wall, a sheet of galaxies stretching for roughly 500 million light-years. Subsequent surveys mapped larger and larger volumes, progressively filling in the picture of the cosmic web at ever greater scales and with ever greater detail. What causes the cosmic web to form? The answer involves dark matter in a fundamental way. In the early universe, shortly after the Big Bang, matter was distributed nearly uniformly throughout space. But nearly uniformly is not perfectly uniformly. There were tiny fluctuations, regions slightly denser than average and regions slightly less dense than average, imprinted on the early universe by quantum processes during an extremely brief period of rapid expansion called inflation. Under the influence of gravity, these tiny fluctuations grew over time. Regions that were slightly denser than average attracted more matter, becoming denser still. Regions that were slightly less dense than average lost matter, becoming emptier. This process, called gravitational instability, operated over billions of years to transform the nearly smooth early universe into the richly structured cosmic web we observe today. Dark matter played a decisive role in this process, for a reason that comes down to timing. In the early universe, ordinary matter was coupled to radiation. The photons that filled the early universe exerted radiation pressure on ordinary matter, preventing it from clumping on small scales. Dark matter, which does not interact with radiation, was free to begin clumping earlier. Dark matter, overdensities formed first, creating gravitational wells into which ordinary matter later fell once it decoupled from radiation. This sequence matters enormously. If only ordinary matter existed, the structures we see today could not have formed in the time available. The universe is roughly 13.8 billion years old. For the observed level of large-scale structure to develop through gravitational instability, starting from the tiny fluctuations seen in the early universe, you need the head start that dark matter provides. Dark matter began building structure while ordinary matter was still being held smooth by radiation pressure. By the time ordinary matter was free to clump, it had a pre-existing dark matter scaffolding to fall into. The cosmic web that we observe today is, in this sense, a fossil record of dark matter's early influence. The filaments, nodes, and voids we see in galaxy surveys trace the underlying dark matter distribution, which itself reflects the pattern of density fluctuations laid down in the first moments of the universe's existence. Mapping the cosmic web is, indirectly, mapping the distribution of dark matter across cosmic scales. Computer simulations have played a central role in understanding the cosmic web. The Millennium simulation, completed in 2005, followed the gravitational evolution of more than 10 billion dark matter particles from the early universe to the present day, in a simulated volume roughly 2 billion light-years across. The structure that emerged from this simulation was strikingly similar to the observed cosmic web, with filaments, clusters, and voids in the right proportions and at the right scales. Subsequent simulations with higher resolution and larger volumes have refined this picture further. These simulations do not simply assume that dark matter produces the right structure. They start from the observed properties of the early universe, measured from the cosmic microwave background, and evolve those initial conditions forward using only gravity. The fact that they produce something closely resembling the observed cosmic web is a powerful confirmation that the dark matter model is on the right track. The voids of the cosmic web deserve special attention. These enormous empty regions, hundreds of millions of light-years across, are not entirely empty. They contain a small number of galaxies, typically smaller and bluer than the galaxies in filaments and clusters. Void galaxies have evolved in relative isolation, without the mergers and interactions that shape galaxies in denser environments. They represent a different evolutionary track, and studying them illuminates how environment shapes galaxy properties. Voids also have a subtle effect on the light passing through them. Light traveling through a void gains a small amount of energy as it enters and loses it as it exits, due to the changing gravitational potential in an expanding universe. This effect, called the integrated Sachs-Wolf effect, has been detected by correlating the pattern of the cosmic microwave background with the positions of large-scale structures, providing an independent line of evidence connecting the cosmic web to cosmological dark matter models. The boundaries between voids, where matter has drained away toward filaments and clusters, are called void walls or sheets. These regions of moderate density contain many galaxies arranged in flattened structures. Our own local group of galaxies, which contains the Milky Way and the Andromeda Galaxy, sits near the edge of a large void, in a region where several filaments converge. Our cosmic address is defined not just by our position within a galaxy, but by our position within this larger structure. Looking at the cosmic web as a whole, what is most striking is how much of space is empty. Voids occupy roughly 80% of the volume of the universe, yet contain only a small fraction of its mass. The matter of the universe, dark and ordinary alike, is concentrated into the thin filaments and dense nodes that occupy the remaining 20% of space. The universe is, by volume, mostly nothing. The web that spans it is thin and widely spaced, and yet that thin web encompasses everything we know. Every galaxy, every star, every planet, every living thing exists within those filaments and clusters. The voids are not places. They are the space between places, the negative space that gives the web its shape. Let the image of the cosmic web accompany you as you drift toward rest. A vast three-dimensional lattice stretching across billions of light-years. Filaments glowing faintly with the light of millions of galaxies. Nodes blazing where filaments cross. And between them, the deep and patient dark of the voids, which are not empty of importance, even if they are nearly empty of matter. The web is the universe's largest structure, and dark matter is its architect. The cosmic microwave background is the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was an opaque plasma, so dense and hot that photons could not travel freely. After that moment, the universe became transparent, and the photons that had been locked in that plasma streamed outward in all directions. We detect those photons today as a faint microwave glow coming equally from every direction in the sky. The cosmic microwave background carries information about the state of the universe at the moment it was released, 380,000 years after the Big Bang. It is a snapshot of the early universe, imprinted with the pattern of density fluctuations that existed at that time, and those fluctuations encode a remarkable amount of information about the composition and properties of the universe, including the amount and nature of dark matter. The temperature of the cosmic microwave background is almost perfectly uniform across the sky, around 2.7 degrees above absolute zero. But almost perfectly uniform is not the same as perfectly uniform. There are tiny variations in temperature from one direction to another, at the level of roughly 1 part in 100,000. These temperature fluctuations reflect the density fluctuations that existed in the early universe. Slightly denser regions were slightly hotter. Slightly less dense regions were slightly cooler. These fluctuations are not random noise. They have a specific statistical pattern, described by what physicists call the power spectrum, which shows how much fluctuation power exists at each angular scale on the sky. The power spectrum of the cosmic microwave background has a characteristic shape with a series of peaks and troughs at specific angular scales. These features are known as acoustic peaks because they arise from acoustic oscillations, sound waves that propagated through the early universe plasma before the moment of last scattering. To understand why these acoustic peaks contain information about dark matter, it helps to understand what was happening in the early universe plasma. In the first 380,000 years, ordinary matter and radiation formed a tightly coupled fluid. Gravity tried to compress regions of higher density, while radiation pressure resisted compression. The result was a series of oscillations, regions alternately compressing and expanding like sound waves in air. At the moment of last scattering, these oscillations were frozen in place, imprinted on the pattern of temperature fluctuations we observe today. Dark matter behaves differently from ordinary matter in this context. Dark matter does not interact with radiation. It does not participate in the acoustic oscillations. It simply contributes to the gravitational potential wells that drive the oscillations without responding to radiation pressure. This difference in behavior means that changing the amount of dark matter changes the pattern of acoustic peaks in the cosmic microwave background in a specific, predictable way. More dark matter deepens the gravitational wells and changes the balance between gravitational compression and radiation pressure. This shifts the relative heights of the acoustic peaks in a characteristic way. By precisely measuring the heights of the first, second, third, and higher acoustic peaks, cosmologists can determine how much dark matter was present in the early universe with considerable precision. The measurements required to extract this information are extraordinarily precise. The Planck satellite, a European Space Agency mission that observed the cosmic microwave background from 2009 to 2013, produced temperature maps of the entire sky with angular resolution and sensitivity far beyond any previous instrument. The acoustic peaks in the Planck power spectrum are measured with enough precision to determine the density of dark matter to within a few percent. The answer from Planck, consistent with earlier measurements from the WMAP satellite and ground-based telescopes, is that dark matter makes up approximately 27% of the total energy content of the universe. Ordinary matter, the kind that makes up stars, planets, gas, and everything we can directly observe, accounts for only about 5%. The remaining 68% is in a form called dark energy, which drives the accelerating expansion of the universe and is an entirely separate mystery from dark matter. This accounting, often summarized as approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, is one of the most important results in modern cosmology. It comes not from studying galaxies or galaxy clusters, but from analyzing the pattern of temperature fluctuations in the oldest light in the universe. The consistency between this cosmological measurement and the astrophysical evidence from galaxy rotation curves, cluster dynamics, and gravitational lensing is among the strongest arguments for the reality of dark matter. The cosmic microwave background also provides information about the nature of dark matter beyond just its total amount. The detailed pattern of acoustic peaks is sensitive to whether dark matter was moving slowly or quickly in the early universe, a distinction that has important implications for how structure formed. Dark matter that was moving slowly, called cold dark matter, would have been able to clump on small scales from early times, producing the hierarchical structure formation we observe, where small structures form first and merge into larger ones. Dark matter that was moving quickly, called hot dark matter, would have smoothed out small-scale fluctuations, producing large structures first. The observed pattern of acoustic peaks, combined with the observed large-scale structure, strongly favors cold dark matter over hot dark matter. The most prominent candidate for hot dark matter is the neutrino, a real particle that exists in enormous numbers but has very small mass. Neutrinos do contribute a small amount to the total mass energy of the universe, but the constraints from the cosmic microwave background and large-scale structure limit their contribution to a small fraction of the total dark matter. Whatever dark matter is, it is not primarily made of the neutrinos we know about. The polarization of the cosmic microwave background provides additional information. Light can be polarized, meaning its electric field oscillates preferentially in one direction, rather than randomly. The scattering of photons off electrons in the early universe plasma produced a specific pattern of polarization in the cosmic microwave background, and measuring that polarization pattern provides independent constraints on cosmological parameters, including the dark matter density. Polarization measurements are more challenging than temperature measurements, requiring even more sensitive instruments, but they have now been achieved with sufficient precision to confirm and refine the temperature-based results. Looking further ahead, future cosmic microwave background experiments aim to measure the polarization with still greater precision, searching for a specific type of polarization signal called B modes, which would be produced by gravitational waves from the inflationary epoch. Detecting this signal would provide information about the energy scale of inflation, which in turn constrains models of the very early universe that may also have implications for dark matter production. For now, the cosmic microwave background stands as one of the most powerful tools for studying dark matter, not by detecting it directly, but by measuring its gravitational influence on the oscillations of the early universe plasma. The pattern of peaks in the temperature power spectrum is a fingerprint of the dark matter content of the universe, and that fingerprint has now been read with enough precision to constrain dark matter's properties in ways that complement and reinforce every other line of evidence. Rest now, and let the image of the early universe settle in your mind. A hot, dense plasma filled with light, sound waves rolling through it, compressing and releasing for 380,000 years, and threaded through all of it, invisible and silent, the dark matter deepening the valleys and shaping the crests of those ancient waves, leaving its signature frozen in the oldest light we can detect. Science often makes progress by elimination, Before settling on the correct answer to a question, it is frequently necessary to rule out the wrong answers systematically, one by one, until only viable possibilities remain. The question of what dark matter is made of has proceeded in this way, and while the correct answer remains unknown, a substantial number of wrong answers have been confidently ruled out. This process of elimination is not a failure. It is progress. Each candidate ruled out narrows the field, sharpens the question, and directs experimental effort toward the possibilities that remain. Understanding what dark matter is not helps clarify what it might be. The simplest and most appealing possibility was always that dark matter is made of ordinary matter, just ordinary matter that is too dim or too diffuse to have been detected. Ordinary matter, in the language of particle physics, is called baryonic matter because most of its mass comes from baryons, the class of particles that includes protons and neutrons. When the dark matter problem first became serious in the 1970s and 1980s, the first candidates considered were populations of dim baryonic objects that might be lurking undetected. These candidates were given the collective name MACOs for massive astrophysical compact halo objects. The category included brown dwarfs, objects too small to sustain nuclear fusion in their cores, which emit very little light. It included old, cold white dwarfs, the remnant cores of dead stars that have faded over billions of years. It included neutron stars and black holes, stellar remnants that are extremely compact and emit negligible radiation. And it included primordial black holes, hypothetical objects that might have formed in the very early universe before any stars existed. The search for MACOs relied primarily on gravitational microlensing. If a compact dark object passed between Earth and a background star, its gravity would briefly focus the star's light, causing a temporary brightening that could be detected by monitoring millions of stars continuously. Several large surveys did exactly this, watching the stars of the Magellanic Clouds and the galactic bulge for years at a time, looking for the characteristic brightening and fading signature of a microlensing event. These surveys found microlensing events, confirming that the technique works, but far fewer events than would be expected if MACOs made up the majority of the dark matter in the halo. The constraints from microlensing surveys rule out MACOs in a wide range of masses as the primary component of dark matter. Very low mass objects produce too short a lensing event to detect. Very high mass objects would produce events that are too rare given the number observed. The intermediate mass range that could plausibly make up most of the halo is largely excluded. Beyond microlensing constraints, there is a more fundamental argument against baryonic dark matter. The abundances of light elements produced in the first few minutes of the universe, a process called Big Bang nucleosynthesis, depends sensitively on the density of baryons at that time. Observations of the abundances of hydrogen, helium, deuterium, and lithium in the oldest, most primitive astronomical objects agree well with the predictions of Big Bang nucleosynthesis for a specific baryon density, and that density is significantly lower than the total matter density required by the cosmic microwave background and large-scale structure. There simply is not enough room for dark matter to be made of baryons without violating these well-tested predictions. The one baryonic candidate that retains some interest is primordial black holes. Black holes formed before nucleosynthesis would not have been counted in the baryon budget, since they would have formed from energy rather than baryons. Primordial black holes in certain mass ranges are not yet definitively ruled out, and they continue to be searched for through gravitational wave detections, microlensing surveys, and other methods. But even if some primordial black holes exist, they are unlikely to account for the majority of dark matter. Neutrinos were the next obvious candidate. Neutrinos are real particles, produced in enormous numbers in the Big Bang and in stars. They have mass, confirmed by observations of neutrino oscillations. They do not interact electromagnetically. They are genuinely dark. For a time, in the late 20th century, they were a serious dark matter candidate. The problem with neutrinos is their speed. Neutrinos are extremely light, and light particles move fast. In the early universe, when structure was forming, neutrinos were moving at or near the speed of light. This means they were hot dark matter, streaming freely and smoothing out density fluctuations on small scales. A universe dominated by hot dark matter would have formed large structures first, which would then fragment into smaller ones in a top-down hierarchy. Observations show the opposite, with small structures forming first and merging into larger ones, a bottom-up hierarchy consistent with cold dark matter. Neutrinos, as a dominant component of dark matter, are ruled out by the observed large-scale structure. The standard model neutrinos are also constrained by their known masses, which are so small that even if all three neutrino species together accounted for their full cosmological contribution, they would make up only a few % of the dark matter. They exist and they contribute, but they are not the answer. A hypothetical cousin of the ordinary neutrino, called the sterile neutrino, is a more viable candidate. Sterile neutrinos would have mass, but would interact even more weakly than ordinary neutrinos, potentially qualifying as cold or warm dark matter depending on their mass. They have not been detected, and constraints from X-ray observations of galaxy clusters have ruled out certain mass ranges, but they remain a possibility worth investigating. What about modifications to gravity? If Einstein's theory of general relativity is not quite right at the low accelerations typical of galactic outskirts, perhaps the flat rotation curves could be explained without invoking any new form of matter. This is the idea behind modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983. MOND modifies the relationship between force and acceleration at very low acceleration values, producing flat rotation curves without any dark matter. MOND is a genuinely interesting idea, and it has some successes. It predicts a specific relationship between the distribution of visible matter and the rotation curve of a galaxy, a relationship called the radial acceleration relation, which has been confirmed observationally. However, MOND struggles to explain the evidence from galaxy clusters, where the mass discrepancy is too large to be accounted for by the MOND modification. It also struggles with the cosmic microwave background power spectrum, which can be fit well by cold dark matter models, but requires additional ingredients in MOND-based frameworks. And it has no natural explanation for the bullet cluster, where mass and gas are spatially separated in a way that dark matter explains cleanly. Relativistic extensions of MOND exist and continue to be developed, but none has achieved the simplicity and explanatory breadth of the cold dark matter model. Most physicists view MOND as an interesting empirical regularity that may reflect an underlying property of dark matter or galaxy formation, rather than a replacement for dark matter itself. The process of elimination leaves us with a clear conclusion. Dark matter is almost certainly not made of ordinary baryonic matter in any form. It is not primarily neutrinos. It is not explained by modifications to gravity alone. What remains are new types of particles, beyond the standard model of particle physics, that have mass and interact gravitationally, but interact very weakly or not at all through the other fundamental forces, In the next chapter, we turn to what these particles might be. For now, as you rest, consider the value of knowing what something is not. The ruled-out candidates are not wasted effort. Each one tested a real possibility, used real data, and gave a real answer. The shape of the remaining possibility space is clearer for each answer received, even when that answer is no. Having ruled out the simplest explanations, physicists have turned their attention to less familiar possibilities. The leading candidates for dark matter are new types of elementary particles beyond anything currently included in the standard model of particle physics. These candidates have been proposed on theoretical grounds, motivated by ideas in particle physics that extend the standard model in various ways, and they make predictions that can, in principle, be tested by experiment. The most extensively studied candidate is a class of particles called weakly interacting massive particles, or WIMPs. The WIMP hypothesis has been attractive for several decades for a reason that goes beyond dark matter itself. Extensions of the standard model of particle physics, particularly a theoretical framework called supersymmetry, predict the existence of new particles with masses roughly comparable to the proton or somewhat heavier, and with interaction strength similar to the weak nuclear force. These particles would be stable and electrically neutral, making them invisible to telescopes. And when physicists calculated how many of these particles would be produced in the hot early universe and how many would survive to the present day, the answer turned out to be remarkably close to the observed dark matter density. This coincidence, sometimes called the WIMP miracle, gave the WIMP hypothesis a strong theoretical motivation. It suggested that the dark matter problem and the hierarchy problem in particle physics, the question of why the weak force is so much stronger than gravity, might have a common solution. A new symmetry of nature, supersymmetry, could solve the hierarchy problem and simultaneously produce a dark matter candidate in the right abundance. That is a compelling combination. WIMPs, if they exist, would interact with ordinary matter through the weak nuclear force, though very rarely. A WIMP passing through a detector on Earth would occasionally collide with an atomic nucleus, depositing a tiny amount of energy that could, in principle, be detected. The signal would be extremely weak, because WIMP interactions are rare by definition, but with a large enough detector, sensitive enough instrumentation, and sufficient shielding from background radiation, detection might be possible. This reasoning motivated the construction of an extensive series of direct detection experiments, which we will discuss in the next chapter. For now, it is worth noting that the WIMP has not yet been detected, despite decades of increasingly sensitive searching. The non-detection has significantly constrained the allowed properties of WIMPs, ruling out many of the simplest supersymmetric models. The WIMP remains a viable candidate, but it is no longer the clear favorite it once appeared to be. A second major candidate is the axion. The axion was originally proposed in the late 1970s, not to solve the dark matter problem, but to solve an entirely different puzzle in particle physics called the strong CP problem. The strong nuclear force, which binds quarks into protons and neutrons, obeys a symmetry between matter and antimatter almost exactly. But the equations of quantum chromodynamics, the theory of the strong force, allow for a violation of this symmetry. The fact that no such violation is observed is puzzling, and one elegant solution involves a new field, the Petequian field, whose quantum excitations are the axions. Axions, if they exist, would be extraordinarily light, billions of times lighter than the electron. They would be produced in the early universe in enormous numbers and would be moving slowly enough to serve as cold dark matter. They would interact extremely weakly with ordinary matter, mostly through a coupling to photons in the presence of a magnetic field. This coupling allows for detection strategies quite different from those used for WIMPs. The axion has gained significant theoretical favor in recent years, partly because the natural parameter space for axion dark matter is not yet excluded, and partly because certain theoretical frameworks, particularly string theory, predict the existence of large numbers of axion-like particles across a wide range of masses. This broader family of particles, sometimes called axion-like particles or ALPs, provides a rich theoretical landscape for dark matter candidates. Sterile neutrinos represent a third class of candidates. The standard model includes 3 species of neutrinos, all of which interact through the weak nuclear force. A sterile neutrino would be a 4th type, one that does not interact through the weak force at all, interacting only gravitationally. Sterile neutrinos could have been produced in the early universe through mixing with ordinary neutrinos, and depending on their mass, they could serve as warm or cold dark matter. Sterile neutrinos are particularly interesting because they offer a potential connection to another puzzle in particle physics, the small but non-zero masses of ordinary neutrinos. In the seesaw mechanism, a popular theoretical framework, the small masses of ordinary neutrinos are explained by the existence of very heavy sterile neutrinos. If the sterile neutrinos involved have masses in a certain range, they could also account for dark matter. This connection between 2 independent puzzles is theoretically appealing, following the same logic as the WIMP miracle. Beyond these leading candidates, a wide range of other possibilities has been proposed. Primordial black holes, discussed in the previous chapter, retain some parameter space. Ultralight axion-like particles, sometimes called fuzzy dark matter, would have masses so small that their quantum wavelength is comparable to the size of a galaxy, producing distinctive effects on small-scale structure that could distinguish them from heavier candidates. Self-interacting dark matter, particles that interact significantly with each other but not with ordinary matter, has been proposed to address certain discrepancies between cold dark matter predictions and observations of small galaxies. There are also more exotic proposals. Some theories suggest that dark matter might be a composite object, built from smaller constituents through a dark version of the strong nuclear force. Others propose that dark matter interacts with ordinary matter through a dark photon, a hypothetical particle that mediates a dark electromagnetic force. The theoretical landscape is genuinely broad, reflecting the fact that the constraints from particle physics alone do not uniquely specify what dark matter should be. What all viable candidates share is a combination of properties. They must have mass, they must be stable on timescales comparable to the age of the universe, they must interact with gravity, and they must interact very weakly or not at all with photons and with the standard model particles that make up ordinary matter. Beyond these requirements, the parameter space of allowed properties is large. The breadth of theoretical possibilities is both a strength and a challenge for the field. It means that many experimental approaches are worth pursuing simultaneously, since different candidates require different detection strategies. It also means that no single negative result definitively rules out dark matter. Each experiment tests a specific range of properties, and a non-detection constrains that range without closing the question. This is a field that lives comfortably with uncertainty, where the honest answer to the question of what dark matter is consists of a list of possibilities, rather than a single name. That is not a weakness. It is an accurate reflection of where the science stands. The evidence that dark matter exists is strong. The evidence for what it is made of has not yet arrived. Both of those things are true, and the experiments described in the next chapter represent the ongoing effort to close that gap. As you rest, let your mind move through these possibilities lightly. Particles so weakly interacting that trillions pass through your body every second without leaving a trace. Particles so light that their quantum nature manifests on the scale of entire galaxies. Objects so ancient they formed before any star existed. The universe has surprised us before with what it contains, and it may surprise us again. The effort to detect dark matter directly is one of the largest coordinated scientific endeavors of the early 21st century. Physicists on several continents have built increasingly sensitive detectors, each designed to catch the rare interaction between a dark matter particle and ordinary matter. Astronomers have searched for indirect signatures of dark matter annihilation or decay in cosmic rays and gamma rays. Engineers at particle accelerators have attempted to produce dark matter particles in high-energy collisions. So far, no confirmed detection has been made, but the limits placed by these experiments have profoundly shaped our understanding of what dark matter can and cannot be. Direct detection experiments aim to observe the recoil of an atomic nucleus struck by a passing dark matter particle. The signal would be tiny, a nucleus kicked with an energy comparable to what a gentle breath might deliver to a grain of pollen. Detecting such a signal in the presence of the constant rain of cosmic rays and natural radioactivity that bombards any detector on the surface of the Earth requires extraordinary measures. The first requirement is shielding. Direct detection experiments are invariably located deep underground, beneath hundreds or thousands of meters of rock. The rock absorbs cosmic rays, which would otherwise produce signals indistinguishable from a dark matter interaction. The experiments are also surrounded by layers of shielding materials, pure water, polyethylene, and lead, to absorb radiation from the surrounding rock and from the detector materials themselves. The second requirement is extreme material purity. Even the smallest trace of a radioactive contaminant in the detector material would produce a flood of background events that would swamp any dark matter signal. The materials used in direct detection experiments are among the purest ever produced, refined to remove radioactive isotopes at the level of parts per trillion or better. Among the most sensitive direct detection experiments are those using liquid xenon as the detector medium. Xenon is well suited for this purpose. It is dense, making it a good target for dark matter interactions, and a particle passing through liquid xenon produces both a flash of scintillation light and a cloud of ionized electrons, two distinct signals that together allow background events to be distinguished from potential dark matter interactions. The Elliott Zeppelin experiment, located in the Sanford Underground Research Facility in South Dakota, beneath nearly 1.5 kilometers of rock, uses 10 tons of liquid xenon and represents one of the most sensitive direct detection experiments ever built. Similar experiments, including Xenon NT at the Gran Sasso Laboratory in Italy and Panda X4T in China, have achieved comparable sensitivity. Together, these experiments have probed the WIMP parameter space to depths that have ruled out many theoretical models and set the most stringent limits, yet on the interaction of dark matter with ordinary matter. Other direct detection experiments use different detector materials. Germanium and silicon crystals cooled to temperatures just above absolute zero can detect the tiny heat deposited by a dark matter interaction alongside an ionization signal. Experiments using these cryogenic detectors, including Super CDMS and CRESST, are sensitive to lower mass dark matter candidates than the xenon experiments, since lighter dark matter particles deposit less energy in a nucleus collision and are better matched to lighter target nuclei. Indirect detection takes a different approach. If dark matter particles are their own antiparticles, as some theoretical models predict, then two dark matter particles that meet can annihilate each other, producing standard model particles as the products. This annihilation should happen wherever dark matter is densely concentrated, and the products, including gamma rays, neutrinos, positrons, and antiprotons, might be detectable by space telescopes and ground-based observatories. The center of the Milky Way is the most obvious target for indirect detection, since the dark matter density is expected to be highest there. The Fermi Gamma Ray Space Telescope has observed the galactic center extensively, and there is indeed an excess of gamma rays in that region that has attracted significant attention. The excess could be consistent with dark matter annihilation, but it could also be explained by a population of millisecond pulsars or other astrophysical sources. Distinguishing between these possibilities remains an active area of research. Dwarf satellite galaxies of the Milky Way are cleaner targets for indirect detection in some respects. They have high dark matter to ordinary matter ratios, low levels of other gamma ray sources, and well understood dark matter density profiles. Fermi observations of dwarf galaxies have placed limits on dark matter annihilation that are competitive with direct detection limits for certain masses and interaction channels. Cosmic rays provide another indirect detection channel. The positron fraction in cosmic rays, the ratio of positrons to the total of electrons and positrons, was measured by the Pamela satellite and later by the AMS-02 experiment on the International Space Station to be rising at energies above roughly 10 gigaelectron volts. This rise could be a signature of dark matter annihilation, producing electron-positron pairs, though it is now more commonly attributed to nearby pulsars, which are known to produce positrons. Collider searches represent a third approach. At the Large Hadron Collider at CERN, protons are accelerated to near the speed of light and collided at energies high enough to produce heavy particles. If dark matter particles exist and interact with standard model particles through any force other than pure gravity, they might be produced in these collisions. Since dark matter would pass through the detector without leaving a signal, the signature of dark matter production at a collider is missing energy. Events where the measured energy and momentum of all observed particles fails to balance, indicating that some unseen particle carried away the remainder. Searches for missing energy signals at the LHC have not yet found evidence for dark matter production, and the results have constrained many WIMP models. However, the relationship between collider limits and direct detection limits depends on assumptions about how dark matter interacts with quarks and gluons, and the two approaches are complementary rather than directly comparable. The Axion, as a much lighter candidate, requires entirely different search strategies. The Axion Dark Matter Experiment, or ADMX, uses a microwave cavity immersed in a strong magnetic field. If axions pass through the magnetic field, they can convert to photons with a frequency corresponding to the axion mass. By tuning the cavity resonance across a range of frequencies and listening for an excess of photons, ADMX searches for axions in a specific mass range. Other experiments use similar principles with different configurations, and the field of axion searches has expanded considerably in recent years. The absence of a confirmed detection, despite all this effort, is itself informative. The simplest WIMP models, particularly those motivated by minimal supersymmetry with masses around 100 gigaelectron volts and weak-scale interaction strengths, are now significantly constrained or excluded. The most natural versions of the theory that originally motivated the WIMP candidate have not been found, and this has encouraged a broadening of the theoretical and experimental landscape. This broadening is healthy. It reflects the scientific process operating as it should, with evidence shaping and redirecting theoretical assumptions. The absence of the most obvious candidate does not mean dark matter does not exist. It means dark matter does not have precisely the properties that the most convenient version of our theoretical frameworks predicted. The universe is under no obligation to provide us with convenient answers. Rest now. Somewhere beneath a kilometer of rock, in a cavern carved from ancient stone, a tank of liquid xenon sits in near-perfect silence, waiting for a signal that has not yet come. The patience required for this kind of science is extraordinary, and it is a form of attention that asks something of all of us who care about these questions. The answer, when it comes, will arrive quietly. The story of how galaxies form is inseparable from the story of dark matter. This is not because dark matter is one ingredient among many in the recipe for galaxy formation. It is because dark matter is, in a fundamental sense, the substrate on which galaxy formation occurs, the scaffolding that determined where galaxies would form, how massive they would become, and when they would begin to assemble their stars. To understand this role, it is useful to go back to the early universe, to a time before any stars or galaxies existed. In the first few 100 million years after the Big Bang, the universe contained no light sources beyond the fading afterglow of the Big Bang itself. This period, before the first stars ignited, is called the Cosmic Dark Ages, and it was during this time that dark matter began laying the foundations for all subsequent structure. In the very early universe, matter was distributed nearly uniformly, with only tiny density fluctuations at the level of 1 part in 100,000. These fluctuations were the seeds of all future structure. Under the influence of gravity, regions that were slightly denser than average began to attract matter from their surroundings. Dark matter, unimpeded by radiation pressure, began this process earlier than ordinary matter. Dark matter over densities grew first, forming the initial gravitational wells that would later accumulate ordinary matter. By the time the universe was a few 100 million years old, the dark matter had organized itself into a hierarchy of halos. Small halos formed first, then merged with each other to form larger halos, which merged again into still larger halos. This process, called hierarchical structure formation, proceeded continuously and produced the nested hierarchy of halos and subhalos that characterizes the dark matter distribution today. As dark matter halos grew, they drew in ordinary matter, primarily hydrogen and helium gas that had been produced in the Big Bang. This gas fell into the gravitational potential wells of the dark matter halos, heating up as it fell. To form stars, the gas needed to cool, radiating away the energy it had gained from falling. The ability of gas to cool efficiently depends on its density and temperature, and it is in the smallest, densest halos that cooling happened most easily in the early universe. Within those first halos, cooled gas collapsed further, reaching densities high enough for the first stars to ignite. These first stars, called population 3 stars, were likely very massive, containing perhaps hundreds of solar masses, and they lived short, violent lives before exploding as supernovae. Their explosions enriched the surrounding gas with the first heavy elements produced by nuclear fusion, and those heavy elements changed the cooling behavior of the gas in subsequent generations of star formation. The mass of the dark matter halo in which a galaxy forms has a profound influence on the properties of that galaxy. In the smallest halos, star formation is often suppressed by several processes. Ultraviolet radiation from early stars can ionize the gas in low-mass halos, preventing it from cooling and forming new stars, a process called reionization feedback. Supernova explosions can drive gas out of small halos altogether, since the gravitational potential of a low-mass halo is not deep enough to retain gas that has been heated and accelerated by a supernova blast. The result is that many low-mass halos never form substantial galaxies, remaining as dark matter subhalos with little or no visible content. In halos above a certain mass threshold, the gravitational potential is deep enough to retain gas against these feedback processes, and galaxy formation proceeds more efficiently. As the halo mass increases, the galaxy it hosts tends to become more massive, more luminous, and richer in heavy elements from successive generations of star formation. The relationship between halo mass and galaxy properties is a central subject of modern observational and theoretical astrophysics. At the high mass end of the halo distribution, in the most massive halos hosting galaxy clusters, a different set of processes suppresses star formation. The gas in a massive halo is too hot to cool efficiently, remaining as a diffuse X-ray emitting plasma rather than condensing into stars. Even where some cooling does occur, the supermassive black holes at the centers of the largest galaxies inject energy into the gas through jets and outflows, a process called AGN feedback, which further inhibits cooling and star formation. The result is that the most massive galaxies are red and dead, their star formation having been quenched billions of years ago. This pattern, suppressed star formation, in the smallest and largest halos with peak efficiency at intermediate masses, is called the stellar-to-halo mass relation, and explaining it is one of the central challenges of galaxy formation theory. The shape of this relation encodes the cumulative effect of all the feedback processes that regulate star formation, and matching it in simulations requires careful modeling of stellar winds, supernovae, and black hole accretion. The connection between dark matter, halo properties, and galaxy properties extends beyond just the mass. The spin of a dark matter halo, imparted by tidal torques from neighboring structures during its assembly, influences the size and structure of the disk galaxy that forms within it. The merger history of a halo, how many smaller halos have merged into it over time and when, influences whether the resulting galaxy is a smooth elliptical or a disk with spiral structure. The environment of a halo, whether it sits in a filament, a cluster, or an isolated region, shapes the gas supply available for star formation and the frequency of interactions with other galaxies. Modern cosmological simulations attempt to capture all of these processes simultaneously, following the gravitational evolution of dark matter alongside the complex hydrodynamics of gas, the formation and death of stars, and the growth of black holes in volumes large enough to contain representative populations of galaxies. The illustrious TNG simulation, for example, follows the evolution of more than 30,000 galaxies across a simulated volume 300 million light-years across, reproducing many observed properties of the galaxy population with impressive fidelity. These simulations are not just computational exercises. They are a way of testing whether our understanding of all the relevant physical processes, including dark matter, is complete enough to reproduce the universe we observe. The fact that simulations including cold dark matter, with realistic treatments of ordinary matter physics, produce galaxy populations that resemble the observed universe is one of the most compelling arguments that the basic framework is correct. As you drift toward sleep, consider the long arc from the nearly smooth early universe to the rich diversity of galaxies we see today. Everything that exists, from the smallest dwarf galaxy to the most massive cluster, was shaped by the prior existence and gravitational influence of dark matter. The visible universe is an elaboration on a dark matter skeleton, flesh on an invisible frame. The light we see is secondary. The structure came first, and it came from the dark. Two of the most important unresolved problems in modern physics share the word dark. Dark matter and dark energy both refer to components of the universe that cannot be seen directly. Both were inferred from their gravitational effects on visible matter and on the expansion of space. Both are unknown in their fundamental nature, and yet they are profoundly different from each other in almost every other respect, and understanding the distinction between them is essential for a clear picture of the universe. Dark matter, as we have explored throughout this journey, behaves like matter. It has mass. It clumps under gravity. It participates in the formation of structure. It can be thought of, at least conceptually, as a kind of substance, even if that substance is made of particles we have not yet identified. Dark matter pulls things together. It is the reason galaxies hold themselves in their shapes, the reason clusters remain bound, the reason the cosmic web has the filamentary structure it does. Gravity is dark matter's primary mode of action, and the effects of dark matter are all gravitational effects of the attractive kind. Dark energy is something else entirely. It is not a substance in the usual sense. It does not clump. It does not participate in the formation of galaxies or halos. It is better described as a property of space itself, an energy that is associated with the vacuum, with the sheer existence of empty space, rather than with any particle or field in the conventional sense. And unlike dark matter, which attracts, dark energy repels. It drives an accelerating expansion of the universe, pushing space apart at an ever-increasing rate. The evidence for dark energy came from observations of distant supernovae in the late 1990s. Type 1. A supernovae are thermonuclear explosions of white dwarf stars, and they have a fairly consistent intrinsic brightness, making them useful as standard candles for measuring cosmic distances. Two independent teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, measured the apparent brightnesses of distant supernovae and compared them with their redshifts to determine how the expansion rate of the universe has changed over time. The expectation, given a universe containing only matter, was that the expansion should be slowing down. Gravity should be pulling matter together and decelerating the overall expansion. What the supernova teams found instead was that distant supernovae were fainter than expected, meaning they were farther away than a decelerating expansion would predict. The expansion of the universe was not slowing down. It was speeding up. Something was driving an acceleration of the cosmic expansion, and that something was named dark energy. The simplest description of dark energy is Einstein's cosmological constant, a term that Einstein himself introduced into his equations of general relativity and later called his greatest blunder, having added it to produce a static universe before the expansion of the universe was known. The cosmological constant represents a constant energy density of empty space, unchanged as the universe expands. When space expands and more space is created, more dark energy comes with it, maintaining a constant density. This self-replenishing property gives dark energy its ability to drive accelerating expansion indefinitely. The cosmological constant interpretation of dark energy fits the observational data well. The cosmic microwave background, combined with large-scale structure and supernova data, produces a consistent picture in which dark energy accounts for approximately 68% of the total energy content of the universe. This is the concordance cosmology, sometimes called the lambda CDM model, where lambda refers to the cosmological constant and CDM refers to cold dark matter. Within this model, dark matter and dark energy play complementary roles across cosmic time. In the early universe, dark matter dominated over dark energy. Dark matter's gravitational influence drove the formation of structure, the growth of halos, and ultimately the formation of galaxies. As the universe expanded, the density of dark matter decreased because the same amount of matter was spread across an ever larger volume. The density of dark energy, by contrast, remained constant. Eventually, roughly 5 billion years ago, dark energy began to dominate over matter, and the expansion of the universe began to accelerate. We live in the era of dark energy domination. The accelerating expansion is pulling galaxy clusters apart over billions of years, eventually stretching the space between them so much that distant galaxies will recede beyond our observable horizon. In the very far future, a hypothetical observer in the Milky Way would look out at a universe that appeared much emptier than ours, with fewer visible galaxies, the rest having been carried beyond the cosmic horizon by the accelerating expansion. Dark matter and dark energy do interact with each other indirectly through their joint influence on the expansion history of the universe and on the growth of structure. The rate at which dark matter halos and clusters grow depends on the competition between gravitational attraction and the accelerating expansion driven by dark energy. If dark energy were stronger, structure formation would be suppressed. If it were weaker, the cosmic web would be denser and more evolved. The observed level of large-scale structure reflects the particular balance between these two components that our universe has achieved. One of the most active areas of current observational cosmology is measuring how this balance has changed over cosmic time through surveys that map the distribution of galaxies across large volumes and at a range of distances. The growth rate of structure as a function of redshift is sensitive to the properties of dark energy. If dark energy is not a simple cosmological constant but something more dynamic, a field whose energy density changes over time, its effects on structure growth would differ from the constant case in ways that upcoming surveys may be able to detect. There is a deep theoretical puzzle associated with dark energy that deserves mention, even if it cannot be resolved here. Quantum field theory predicts that empty space should have an energy density associated with the zero-point fluctuations of all quantum fields. When physicists calculate this predicted vacuum energy using standard methods, the answer is vastly larger than the observed value of the cosmological constant. The discrepancy is enormous, perhaps the largest discrepancy between a theoretical prediction and an observation in all of science. Explaining why the observed dark energy density is so small, when quantum field theory predicts it should be so large, is called the cosmological constant problem, and it remains entirely unsolved. This puzzle is a reminder that while we have characterized dark energy observationally and incorporated it into our cosmological model, we do not understand it. It sits in our equations, it fits our data, and we have no idea what it fundamentally is. In this respect, dark energy and dark matter share a deeper similarity than their differences might suggest. Both are names we have given to our ignorance, labels attached to observational facts that await a deeper explanation. The universe is, in its bulk composition, a thing we do not understand. 5% of it is ordinary matter, the kind we can see and touch and build theories about. The remaining 95% is dark matter and dark energy combined, both unknown at the fundamental level, both inferred from their effects rather than directly detected. That is the honest picture of where cosmology stands, and it is, if one pauses to consider it, both humbling and remarkable. As you rest, carry that thought lightly. The universe is mostly a mystery, and yet, from within that mystery, using only the thin thread of light that reaches our instruments, we have learned enough to say what fraction of everything is unknown, and to characterize how that unknown behaves. That is not a small achievement. Throughout this exploration, we have largely accepted the dark matter interpretation of the observational evidence. This is appropriate because dark matter is the mainstream scientific consensus and is supported by an impressive convergence of independent lines of evidence. But science is not served by presenting consensus as if alternatives do not exist or have not been seriously considered. Modified gravity theories represent a genuine alternative research program, pursued by thoughtful physicists, and understanding why most cosmologists find them insufficient illuminates why the dark matter interpretation is as robust as it is. The original modified Newtonian dynamics proposal, put forward by Mordechai Milgram in 1983, starts from an observation about galaxy rotation curves that is, on its face, striking. Not only are the rotation curves of galaxies flat, but the point at which they begin to deviate from Keplerian behavior corresponds to a specific very small acceleration. Below a certain acceleration threshold, roughly 1/10 billionth of the acceleration due to gravity at Earth's surface, the gravitational force experienced by an object appears to be stronger than Newton's law predicts. Milgram proposed that below this acceleration threshold, the effective gravitational force scales differently with distance than Newton's inverse square law. In MOND, the acceleration experienced by an object in a gravitational field depends on the square root of the Newtonian acceleration, when that acceleration is very small. This modification naturally produces flat rotation curves for any galaxy, because the outer regions of galaxies are precisely in the regime where accelerations are small. The MOND modification makes a specific and testable prediction. For any galaxy, knowing only the distribution of visible matter, you should be able to predict the rotation curve using MOND's formula. This prediction has been tested for hundreds of galaxies, and the results are impressive. MOND correctly predicts rotation curves for a wide variety of galaxy types and masses, including cases where the rotation curve has unusual features that reflect unusual distributions of visible matter. This predictive success is the strongest argument in MOND's favor. It is not a small thing. The ability to predict the detailed shape of rotation curves from visible matter alone, without fitting any additional free parameters for each individual galaxy, goes beyond what the standard dark matter model easily achieves. In the dark matter model, the rotation curve of a galaxy depends on both the visible matter and the dark matter halo, and the halo properties must generally be inferred from the data rather than predicted in advance. However, MOND faces serious difficulties on scales larger than individual galaxies. In galaxy clusters, the mass discrepancy is too large to be explained by MOND's modification. Even with MOND, the observed velocities of galaxies in clusters require more mass than the visible matter provides. Some MOND proponents have suggested that the additional mass could be in the form of ordinary but undetected baryonic matter, such as cold gas clouds or dim stars. This is possible in principle, but it reintroduces a missing mass problem that MOND was supposed to eliminate. The cosmic microwave background poses a deeper challenge. The pattern of acoustic peaks in the CMB power spectrum as discussed earlier, is exquisitely sensitive to the ratio of dark matter to ordinary matter in the early universe. Standard cold dark matter models predict the observed peak pattern accurately. MOND, being a modification of gravitational dynamics rather than an addition of new matter, cannot reproduce this pattern without significant additions to the theory. Relativistic extensions of MOND, such as tensor vector scalar gravity and its successors, have been developed to address the cosmic microwave background and other relativistic phenomena. These theories are considerably more complex than the original MOND proposal, introducing additional fields and free parameters. They can be made to fit the CMB data, but only with careful tuning, and they lose the simplicity that made MOND appealing in the first place. The bullet cluster and similar merging cluster systems present perhaps the most direct challenge to MOND-like theories. In these systems, as discussed, the total mass distribution as revealed by gravitational lensing is separated from the ordinary matter distribution revealed by X-ray observations. In the dark matter picture, this separation arises naturally because dark matter does not interact electromagnetically and pass through the collision without slowing. In MOND, the gravitational field is a modification of the fields produced by ordinary matter, so the gravitational effects should follow the ordinary matter. The observed separation of mass from gas is difficult to reproduce. Several modified gravity theorists have proposed that even within MOND-like frameworks, the presence of ordinary matter on one side of the collision modifies the effective gravity on the other side through a non-linear effect, potentially reproducing some of the observed separation. The details of these arguments are complex and contested. Most physicists find them less convincing than the dark matter explanation, but they illustrate that the modified gravity community has not simply conceded the bullet cluster argument. There is a perspective from which MOND and dark matter are not necessarily in opposition. Some theoretical proposals suggest that dark matter may have properties that naturally produce MOND-like behavior in the regime of low accelerations. Superfluid dark matter, for example, proposes that dark matter condenses into a superfluid state in the inner regions of galaxies, and that the phonons of this superfluid mediate an additional force that mimics MOND. If correct, this would explain both the large-scale successes of dark matter and the small-scale successes of MOND within a single framework. This kind of synthesis, where apparently competing explanations turn out to be different aspects of the same underlying physics, is not uncommon in the history of science. It may or may not be the right path here, but it illustrates that the debate between dark matter and modified gravity is not simply a debate between correct and incorrect. It is a debate about which aspects of the observational evidence are most fundamental and what kind of explanation best unifies them. For now, the weight of evidence favors dark matter over pure modified gravity. The CMB, large-scale structure, galaxy clusters, and the bullet cluster all fit more naturally within the dark matter framework. The rotation curve successes of MOND remain something that any complete theory of dark matter and galaxy formation should explain or reproduce. The most productive attitude is to hold both the strength of the dark matter evidence and the genuine puzzles that MOND identifies, allowing each to inform and sharpen the other. As you rest, let the tension between these frameworks be a peaceful one. Science progresses through productive disagreement as much as through consensus. The researchers who pursue modified gravity are asking important questions, and the answers they receive, whether confirming or refuting their proposals, advance the field. After several hours exploring the evidence for dark matter, its distribution in galaxies and clusters, its role in shaping the cosmic web and driving galaxy formation, and the leading candidates for what it might be, it is worth pausing to take stock of what genuinely remains unknown. The field has made remarkable progress in the past century. It has also accumulated a set of unresolved tensions and open questions that honest science requires acknowledging. The most fundamental unknown is the identity of dark matter. Despite decades of searching with increasingly sensitive instruments, no direct detection of a dark matter particle has been confirmed. The WIMP, once the leading candidate, has not been found in the parameter space that the simplest theoretical models predicted. The axion has not been detected, though the search has not yet covered the most theoretically favored mass range. No dark matter signal has emerged from collider experiments, indirect detection surveys, or any other observational channel with sufficient clarity to constitute a confirmed discovery. This non-detection is not a reason to doubt that dark matter exists. The gravitational evidence for its existence is overwhelming and comes from too many independent sources to be dismissed. But the non-detection does mean that dark matter, whatever it is, does not interact with ordinary matter in any of the simple ways that were most convenient to test. Either dark matter interacts more weakly than the most straightforward WIMP models predicted, or it interacts through channels that current experiments are not sensitive to, or the dark matter candidate is something other than the particles that have been most extensively searched for. The small-scale structure of the universe presents a cluster of related puzzles that the standard cold dark matter model has not fully resolved. The missing satellites problem noted that the Milky Way has far fewer satellite galaxies than cold dark matter simulations predict. The too big to fail problem noted that the most massive subhalos predicted by simulations appear to be too concentrated to match the observed properties of the Milky Way's brightest dwarf satellites. The core cusp problem noted that simulations predict dark matter density profiles that rise steeply toward the center of galaxies, while observations of some dwarf galaxies suggest flatter central profiles. These tensions have been discussed for 2 decades, and partial resolutions have been proposed. Baryonic feedback, particularly the explosive energy released by supernovae, can expel gas from the centers of small galaxies, reducing the central dark matter density and transforming a cuspy profile into a chord one. Rayonization can suppress star formation in small halos, explaining why many predicted subhalos are dark. Improved observational techniques continue to find new faint dwarf galaxies around the Milky Way and other nearby galaxies, reducing the severity of the missing satellites problem. Whether these baryonic explanations are sufficient to resolve all of the small-scale tensions, or whether the tensions indicate that dark matter has properties beyond the simplest cold dark matter model, remains an open question. Self-interacting dark matter, warm dark matter, and fuzzy dark matter have all been proposed as modifications that could ease small-scale tensions while preserving the large-scale successes of the cold dark matter framework. None of these alternatives has been confirmed, and none has fully replaced standard cold dark matter as the preferred model. The Hubble tension is an unresolved discrepancy that may or may not be connected to dark matter. The Hubble constant measures the current rate of expansion of the universe. 2 independent methods of measuring it give results that disagree at a statistically significant level. Measurements based on the cosmic microwave background and the physics of the early universe give a lower value for the Hubble constant. Measurements based on the local universe, using supernovae and other distance indicators, give a higher value. The discrepancy has persisted as measurements have become more precise, suggesting it may reflect a genuine inconsistency in the standard cosmological model rather than measurement error. Some proposed resolutions to the Hubble tension involve modifications to the dark matter or dark energy components of the Standard Model. For example, by introducing a new form of energy that was present in the early universe and has since diluted away, called early dark energy. Whether dark matter physics is implicated in this tension remains to be determined, but the tension itself is a genuine challenge to the current concordance model. The nature of dark energy remains as mysterious as ever. The cosmological constant interpretation fits the data, but the theoretical puzzle of why the vacuum energy is so much smaller than quantum field theory predicts has not been resolved. If dark energy is not a cosmological constant, but a dynamic field, future surveys may detect its evolution over time, providing clues to its nature. The relationship between dark matter and ordinary matter is also imperfectly understood. The ratio of dark matter to ordinary matter in the universe today is approximately 5:1. Why this ratio has this particular value, rather than any other, is not explained by the Standard Model. The mechanisms that produced both the ordinary matter abundance and the dark matter abundance in the early universe may be connected, and understanding that connection could illuminate both. The question of whether dark matter has any self-interactions remains open. The simplest models assume that dark matter particles interact with each other only through gravity. But self-interacting dark matter, where dark matter particles also scatter off each other through a dark force, could address some small-scale structure tensions while being consistent with constraints from merging clusters. The allowed level of self-interaction is constrained but not yet pinned down. Finally, the possibility that dark matter is not a single component, but a mixture of different particles, analogous to how ordinary matter contains many different particle species, has not been explored exhaustively. A dark sector with its own internal structure, including particles of different masses and different interaction properties, is a theoretically rich possibility that the current observational constraints do not rule out. These open questions are not signs of failure. They are signs of a field that has learned enough to identify what it does not yet know. The history of physics is full of periods where the evidence pointed clearly to the existence of something without yet revealing its nature. The electron was known to exist before its quantum mechanical properties were understood. The neutrino was postulated decades before it was detected. The Higgs boson was predicted and searched for nearly 50 years before its discovery. Dark matter may follow a similar trajectory. The evidence for its existence is clear. The question of its nature is waiting for an answer that experimental and observational science has not yet delivered. That gap between clear evidence and unknown identity is where the field lives right now, and it is a productive and energetic place to live. Rest now, and let the open questions be comfortable rather than troubling. The universe does not become less ordered because we do not yet understand all of it. What remains unknown is an invitation, not a problem. The next decade promises to be one of the most productive in the history of dark matter research. A new generation of experiments, observatories, and theoretical tools is coming online or being planned, each designed to probe dark matter in ways that were not previously possible. Even if no single experiment delivers a definitive detection, the combined output of this new generation will significantly sharpen our understanding of what dark matter can and cannot be. In direct detection, the next generation of liquid xenon experiments will extend the sensitivity of WIMP searches by roughly an order of magnitude beyond current limits. The proposed XLZD consortium, which would combine the resources of the LUX-Zeppelin, Xenon NT, and Pandax collaborations into a single next-generation experiment with a 40 to 60 ton xenon target, would push sensitivity deep into the region where an irreducible background from solar and atmospheric neutrinos begins to limit further progress. This neutrino, flaw, or more accurately, the neutrino fog, represents the point at which dark matter signals become difficult to distinguish from neutrino interactions. But it is not an absolute barrier, and techniques for navigating it are being developed. If WIMPs exist at masses and interaction strengths within reach of these next-generation experiments, detection would be nearly certain. If they remain undetected even then, the simplest WIMP models would be definitively excluded over a wide range of masses, forcing a significant rethinking of the theoretical landscape. The axion search is entering an era of rapid expansion. The ADMX experiment continues to scan the mass range most favored by the simplest axion models, and new experiments using different cavity designs, different detection techniques, and sensitivity to different axion masses are proliferating. The CASPER experiment searches for axion-induced effects on nuclear spins. The Abracadabra and DM radio experiments use lumped element resonators sensitive to ultralight axions. The IAXO helioscope will search for axions produced in the Sun. Together, these experiments are beginning to survey the broad mass range over which axions might exist, and over the next decade, they will cover much of the theoretically motivated parameter space. On the observational side, several major new facilities will dramatically expand our ability to map dark matter through its gravitational effects. The Vera Rubin Observatory, formerly the Large Synoptic Survey Telescope, began science operations recently and will spend a decade imaging the entire southern sky repeatedly, building up a catalogue of billions of galaxies suitable for weak gravitational lensing analysis. The resulting dark matter maps will cover an enormous fraction of the observable universe with unprecedented detail. The Euclid Space Telescope, launched by the European Space Agency, will conduct a wide-field survey of galaxy shapes and positions spanning billions of light-years, combining weak lensing and galaxy clustering measurements to constrain dark matter and dark energy properties simultaneously. The Roman Space Telescope, planned by NASA, will complement Euclid with deep imaging over smaller fields, accessing higher redshift galaxies and enabling independent cross-checks. These surveys will test the cold dark matter model with a precision that current data cannot match. They will measure how the growth of structure depends on redshift, test the predictions of dark matter simulations on a range of scales, and potentially detect subtle signatures of dark matter self-interactions or other deviations from the simplest model. They will also provide the most precise measurements yet of the Hubble constant from large-scale structure, potentially resolving or deepening the Hubble tension. In gamma-ray astronomy, the Cherenkov Telescope Array, a ground-based observatory consisting of hundreds of individual telescopes working together, will observe the sky at very high gamma-ray energies with sensitivity far exceeding current instruments. It will search for dark matter annihilation signals from the galactic center, dwarf galaxies, and galaxy clusters over a broad range of dark matter masses and annihilation channels. Combined with continued operation of the Fermi Gamma Ray Space Telescope, it will provide comprehensive coverage of the indirect detection parameter space for heavy dark matter candidates. Gravitational wave astronomy opens an entirely new window on dark matter. If primordial black holes contribute significantly to dark matter, the LIGO, Virgo, and CAGRA detectors should eventually see mergers of these objects, with characteristic mass distributions that would distinguish them from black holes formed by stellar collapse. The planned Laser Interferometer Space Antenna, LISA, will extend gravitational wave astronomy to lower frequencies, sensitive to mergers of massive black holes and to a range of exotic, early universe signals that could be connected to dark matter production. Theoretical progress is also expected on multiple fronts. Machine learning techniques are increasingly being applied to the analysis of cosmological simulations and observational data, enabling the extraction of more information from existing datasets and the identification of subtle patterns that traditional analysis methods might miss. Emulators, fast approximations to expensive simulations, are making it possible to explore large regions of theoretical parameter space efficiently, accelerating the comparison of models with data. The interface between particle physics and cosmology will continue to be fertile ground. If the Large Hadron Collider is upgraded as planned, its higher luminosity will enable more sensitive searches for dark matter production and for the new physics that dark matter candidates like supersymmetric particles would signal. Proposed future colliders operating at higher energies would extend this reach further still. Perhaps the most significant theoretical development of the next decade will be a greater integration of different lines of evidence. The picture of dark matter that emerges from direct detection experiments, from indirect detection surveys, from gravitational lensing maps, from the cosmic microwave background, and from the detailed properties of dwarf galaxies must all be consistent. As each of these channels provides more precise information, the constraints on dark matter properties will become jointly more powerful, narrowing the allowed parameter space from multiple directions simultaneously. There is a reasonable possibility that within the next decade, one of these approaches will deliver a signal. A direct detection experiment might observe an excess of nuclear recoil events above background. An indirect detection survey might identify a gamma ray or neutrino signal from the galactic center that cannot be explained by known astrophysical sources. An axion experiment might detect the conversion of axions to photons in its resonant cavity. A gravitational wave observatory might see a population of black hole mergers with a mass distribution inconsistent with stellar evolution. Any of these signals, if confirmed by independent experiments and shown to be consistent with dark matter properties inferred from other observations, would represent one of the most significant scientific discoveries in history. The identification of what dark matter is made of would complete a picture that began with Zwicky's observation of galaxy clusters in 1933, continued through Rubin's rotation curve measurements in the 1970s, was elaborated by the cosmic microwave background measurements of the 2000s and 2010s, and has been sustained by decades of patient, careful, collaborative science. That completion may come soon, or it may require another generation of experiments, another generation of scientists, another generation of patients. Either way, the science is alive, the instruments are improving, and the question remains one of the most important in all of physics. We have traveled a long way together tonight, from the motion of galaxies in clusters to the acoustic oscillations of the early universe, from the rotation curves of spiral galaxies to the architecture of dark matter halos, from the landscape of dark matter candidates to the experiments quietly searching for them beneath mountains of rock. It is fitting, at the end of this journey, to step back from the details and consider what all of this tells us about our place in the universe. The universe is, by mass, mostly something we do not understand. Ordinary matter, the kind that makes up every atom in your body, every star in the sky, every planet, every cloud of gas between the galaxies, accounts for approximately 5% of the total energy content of the universe. Dark matter accounts for another 27%. Dark energy accounts for the remaining 68%. The visible universe, everything that has ever been seen through any telescope, represents a small minority of what, exists. This is a remarkable situation to be in. For most of human history, the universe was what could be seen: stars, planets, the occasional comet, then galaxies, and the realization that the universe was far vaster than imagined, then the expanding universe, and the understanding that everything we see is rushing away from everything else. And now this, the understanding that what we see, everything that has ever reflected or emitted light, is a thin, bright layer on top of a much larger dark foundation. There is something in this that asks for a particular kind of equanimity. It would be easy to feel diminished by it, to feel that the visible universe, and by extension everything familiar and knowable, has been demoted from its central place. But another way to receive this information is with a kind of wonder at the scale of what remains to be discovered. We live at a moment in history when the existence of dark matter is established, but its nature is unknown. That is a remarkable position to occupy, a moment of knowing enough to define the question precisely, while not yet knowing the answer. Consider the dark matter halo of the Milky Way, extending perhaps 600,000 light-years in every direction from where you are right now. It is all around you, passing through you, constituting the greater part of the mass of the galaxy you call home. You cannot see it. You cannot feel it. Your body is entirely transparent to it. And yet it is there, and its gravity is part of what holds your galaxy together. What makes the night sky what it is rather than a scattering of isolated stars with nothing to bind them? Consider the cosmic web, the vast network of filaments and voids that organizes the large-scale structure of the universe across billions of light years. Most of the mass in those filaments is dark matter. The scaffolding of the universe is invisible. The visible matter, the galaxies and clusters that trace the filaments like dew on a spider web, is a decoration on a structure we cannot see. Consider the early universe, 380,000 years old, filled with the sound of acoustic oscillations rolling through the plasma, waves of compression and rarefaction moving at a third of the speed of light. Threading through all of that sound and light was dark matter, shaping the gravitational landscape in which those oscillations played out, leaving its fingerprints in the pattern of temperature fluctuations that we still detect today as the cosmic microwave background. The oldest signal in the universe carries the imprint of dark matter. Consider the first stars, igniting in small dark matter halos several 100 million years after the Big Bang. Without those halos, without the gravitational wells that dark matter provided, the gas of the universe would have remained too diffuse and too uniformly distributed to collapse into stars at all. Every star that has ever existed, every star that exists now, every star that will exist in the future, formed within a dark matter halo. Darkness was the prerequisite for light. There is a philosophical dimension to all of this that science alone cannot fully resolve. Dark matter raises questions about the reliability of our intuitions. We are accustomed to trusting our senses, to taking the visible world as the real world. The existence of dark matter is a reminder that the visible world is not the whole world, that the universe contains substances and structures that are real and consequential, without being perceptible to any of our unaided senses or any of our instruments based on electromagnetic radiation. This is not a new lesson. Physics has been teaching it for over a century. Atoms were invisible for most of the history of science, their existence inferred from chemistry and Brownian motion, long before they could be directly imaged. Neutrinos pass through the entire Earth without stopping. Gravitational waves distort space by less than the diameter of a proton over distances of kilometers. The universe has repeatedly turned out to contain things that our senses cannot directly access. Dark matter is the largest known instance of this pattern. Not just a new type of particle, but a new type of matter that constitutes the majority of the universe's mass. Its discovery, or rather its inference, represents one of the most significant expansions of the known in the history of science. And yet it remains, in its fundamental nature, unknown. The gravitational evidence is clear. The identity of the substance responsible for that evidence has not yet been established. We know dark matter is there. We know what it does. We do not know what it is. That gap between knowing that and knowing what is where science lives right now, actively, with experiments running, and theorists thinking, and observers cataloguing, and the question very much open. There is a peace in that openness, if you allow it. The universe is not fully explained. There are real questions that real science has not yet answered. That means the story is not finished. It means there are discoveries still to come, surprises still waiting in the data, insights still forming in the minds of people who are working on these problems today. The universe is still yielding its secrets, slowly and on its own terms. As you rest now, let all of this settle gently. The dark matter halo of your galaxy surrounds you. The cosmic web extends in every direction to distances your mind cannot fully hold. The oldest light in the universe carries within it the pattern left by invisible matter in the first moments of time. You exist within a universe that is mostly unknown, mostly dark, and entirely real. The darkness is not empty. It is full of something we have not yet learned to see. That is where we leave it tonight, not with an answer, but with a question held peacefully in the mind, not with a conclusion, but with an open horizon stretching in every direction.